Good evening. So I will talk today just on this title. And I don't have yet real data though, but I just start what I want to do, what we want to do, and then I want to the audience understand what we are going to do. So just asking, do photons shed light on the mechanism? I hope, because the photon is the elementary particle of light. So, but the last conference, ICCF21, we measured the gamma rays in detail and precisely, but no discrete gamma rays are there with excess heat of a nickel copper zirconium plus hydrogen system. So that means no nickel plus proton or the copper plus proton or the nickel plus quasi-neutron, that means proton plus electron, reactions occurred. And no proton plus proton going to deuteron plus positron plus neutrino, because in this case, we should have a 511 keV gamma rays. And neither continuum gamma rays up to, for let's say, more than gamma ray energy more than 50 keV. So actually, in these denial data, of course, narrow the options. But however, still we have to ask, how is locally generated energy transferred to heat? Because we saw this heat, but how? Here, I want to ask the opposite way. The question is tried. What happens if all the energy was taken away by many electrons? So this is just inside the metal. So there's lots of lattice metal ion, and also like free electrons moving around. Those are the conduction electrons. And if you put the energy just in this very narrow region, then what happens? So maybe the energy is distributed to the electrons inside of this circle, then got the energy, very high energy, then just randomly moving around and then losing the energy in that part. So that might be the hot spot. So let us understand what the electron behavior in this low energy region. So there's two main processes of energy loss of electron in material. One is collision loss. This means excitation of a material, atomic excitation, ionization, lattice vibration, etc., etc. So above the 10 keV, the famous Bloch formula can be applied for this region. So this is just the average electron excitation energy. But if the energy of an electron is getting larger, another mechanism will occur. That's a Bremsstrahl, the radiation loss. It's mainly, of course, it's a Bremsstrahl emission. It is associated with the dissolution of electron. And photons in close proximity to the nucleus. And also, as you see, at low energy, the collision process is much higher than the radiation process. Oh, sorry. Let's look at the low energy region more carefully. And this is, in this region, it's not understood very well. But anyhow, these group developed the estimation down to less than 10 electron volt, something around 10 electron volt region. You see the large energy, this is, by the way, this is the electron energy and versus so-called stopping power. That's the energy loss versus distance. So if the 1 keV electrons moving away, the energy loss is just 40 electron volt per nanometer. But in this region, your energy loss is very much increased up to, let's say, 80 electron volt or so. So that means this part, large energy loss contributing the thermal energy. And we can calculate the range of electrons like this plot. So this is the range of electrons. In this case, this is just 1 nanometer and 10 nanometer. And also, you can calculate the stopping time of electron in this energy region. So I would say, if the electron energy less than 2 keV, range is very short. This is something around 40 nanometer at this point. And also the stopping time is very small. This is just around, let's say, less than 200 femtosecond. That means less than 0.2 picosecond. So that means in this, using this mechanism, that region is quickly heated up. And let's see, what does it say? Yeah, I would say the submicron region, it may be the hotspot. And I calculate this using those information, and just assume that just 1 MeV given to the hotspot sphere, and then energetic electrons thermalize small space. Let's say the radius is less than 40 nanometer, and the temperature of hotspot is calculated just a simple estimation. The delta T is the temperature difference between the hotspot and the ambient circumstances. And M is mass and C is specific heat. So if I said hotspot, so that is hotspot should be, the difference should be the more than 100 K. And also this is limited by the boiling temperature, because if the spot is over the boiling temperature, it deleted. So then I calculate this. So this is the radius of hotspot as a function of a number of initial electrons. If you have an initial electron, let's say 1,000, your radius, hotspot radius is something 10 nanometer. And in this case, temperature is very high. So beyond that, no more hotspot. And if the number of the electrons is something like 500, the radius is something like 30 or 40 nanometer, and temperature is something like that. And also, we have to consider about the formation time and the decay time of a spot. The time for local equilibrium, I just calculate the electrons, use the electron stopping time. That means formation time of a spot is something around 50 femtosecond to 200 femtosecond. And the thermal diffusion time constant that's calculated from thermal diffusion constant. And then we can estimate the decay time hotspot. So this is very long comparing to this formation time. And then 1 watt heat production makes a formation rate is something like that, 6 times 10 to 12 per second. Is this observable in a thermal radiation spectrum? This is the next question. Yeah, the thermal radiation is just calculated by using the Planck formula like this. The original Planck formula is a function of wavelength lambda, but I usually use the energy of photons. That is very familiar for us. So if you calculate this, this is the energy of a photon And this is the strength, flux of photons flux. And then if the temperature is changing, of course, the slope is changing. So if you observe this one, you can easily obtain the temperature of the hot spot. So normally, our experiment using the high temperature, something around the 700 K. So there's a base temperature of the foil and also the hot spot temperature. So the ratio of the hot spot to the area ratio of hot spot to the base foil is just given. So I just put let's say 10 to the minus 6 for this ratio. Then you have a base temperature, and if your hot spot has let's say 1000 K, there's some kind of change of a slope, something around here. It is just a visible light region. And also if you change the hot spot more than this one, let's say 10 to minus 4, and then you have the changing point is much lower energy. So therefore, we can conclude that we can observe thermal radiation hotspot, let's say, with a temperature change is more than 300 degrees. And of course, if there was a light, then the observation may provide information on the initial distribution of condensed energy. Let's go to the bremsstrahlung. As said, bremsstrahlung is a continuous energy electromagnetic radiation which accompanies any interaction of charged particles, and its strength depends strongly on the acceleration or deceleration. So we can ask, does a free electron emit a photon in this situation? The answer is no, it cannot emit. The simple explanation is because of the energy momentum conservation. So therefore, we can ask again, how about an electron interacting with a nucleus? And then answer is, of course, yes. Yeah, it can emit gamma rays, photons, since the conservation of law now can be conserved by absorbing the momentum in this nucleus, then the electron can emit photons. But I want to I want to say that the main part of this bremsstrahlung should be electric dipole radiation. Therefore, an electron nucleus collision emits a photon, but an electron collision does not. But anyhow, I calculate this probability by using this formula. So this is the review of a long time ago, though. But this review is very nice. You can find this kind of formula for various energy regions. But anyhow, I calculate using this formula, and then I get the cross section for the one electron. And if you have a 50 keV electron, the spectrum something like this. And this is the cross section is 1 Barn per keV. So therefore, we can make a rough estimate of yield by just using this kind of things. Then I calculate the counting rate, counts per keV. So this 1 Barn corresponding to the, for example, the 100 nanometer nickel case, you have, let's say, 4 times 10 to the minus 12 photons per electrons. That means the counting rate is something like 520 counts per second. Okay, in this case, I just assume all the energy going to the bremsstrahlung, but I need a ratio. Therefore, this must be reduced by the factor put on here. And this ratio, Bremsstrahl's ratio, is easily calculated. And it says just something around 3 times 10 to minus 4. That means we still have a count, let's say 1 count per 100 seconds. That is very enough to measure it. So that should be very interesting. Let's say summarize just at this point, when a huge energy is generated in narrow space in the material and all energy is given to many electrons, what happens? We can expect hot spots on the surface of the tinfoil, and the visible light spectroscopy may show the thermally equilibrated light with higher temperature than ambient. And we can also expect the Bremsstrahlung emitted by electrons with higher energies than 10 keV. And X-ray measurement might clarify maximum energy of electrons for, let's say, electron energy less than 50 keV. But that, of course, we have to ask again, do proton-proton or deuteron reaction allow many energetic electron emissions? Because the nuclear reaction assumed to occur has a very characteristic feature, huge Coulomb barrier between the protons or the deuteron. They are, these particles are forced to travel through, let's say, quantum tunneling. And also the nuclear reaction region is very small and spacey. The interaction radius is something like this order, several femtometers. So this is the future of a nuclear force, of course. On the other hand, conduction electrons in metal are assumed to gain higher energy by the reaction. If you see the density of electrons, the number of valence electron times atom density, therefore, the density is something like this. Just 100 electrons per cubic nanometer. If you calculate the range of nuclear reaction, only the 10 to minus 13, only minus 13 electrons. And also the initial state, almost free electron with a kinetic energy of just several electron volts. This is a Fermi energy, okay? So that only less than 10 to minus 12 electrons in the nuclear reaction volume. How do you get a lot of electrons involved in this reaction? Let's say I need the uncertainty principle to understand. So if, let's assume that A plus A going to B plus gamma, this is a typical nuclear reaction. The A particle, by the way, this is a so-called Feynman diagram. A comes, also another A comes, and get their interaction here, and then get a change to B. So the electron, if the electron interact before this particle A reach to this fusion point, can you put the energy to this one? Yes, the famous uncertainty principle, delta E times delta T, equals about Planck constant. This means during this short range period, this world allows to be violated of energy conservation. 5 minutes, thank you. And therefore, if the energy transfer this, and then within this time range, the fusion occurred, that's all right. So of course, we cannot see this region. So that is why we are saying that this region is just a virtual state. You see, in this period, energy relation of electron and scattering on A as energy conservation is violated, but very small energy. And if you need a delta E 1 MeV, we have to borrow the energy from the future occurring reaction. And then this time should be less than that, just around 10 to minus 12, not a 12, minus 21. It's a very short time. How come? Oh, it is impossible. It's for me. I mean, not for me. Okay? So let's consider about the particle motion under the barrier. So this is a very simple example. The particle is moving away, moving just energy E, and here you have a barrier or the potential. And the particle, in the classical world, the particle cannot punch through this barrier. But at the quantum mechanical world, the particle can punch through by just the wave nature of a particle. And in this region, the particle velocity is defined just by this formula, of course. But in this region, the E is smaller than barrier energy. That means velocity is not a normal number. If you calculate this, you need an imaginary velocity. What is this imaginary velocity or the distance? So therefore, the physicists introduced the imaginary time. That's a tau equals imaginary time, IT. Then the d tau equals IDT. So using this change, the velocity is real, and the space real, and the acceleration real. That's good. But you see that according to this conversion, the particle is just go through along with the real axis, but here the time is changed to imaginary time. And then after that, again, along with the real axis. And a long time ago, I observed the Bremsstrahlung associated with alpha decay. Alpha decay is one of the famous tunneling effect. And we are asking, in this tunneling region, the alpha particle can emit photons or not. And we measured this one. But anyhow, we finally, and just using this picture, and we know that in this region we have, of course, the Bremsstrahlung strength. And in the real time region, we also have real strength. And then what was interesting is these two amplitudes interfere and make a distraction interference. Then the real structure, observed structure is like this. It is very much explained by this formula. So therefore, particle under the barrier move along the imaginary time. How long does a particle stay under the barrier? And the recent studies shows that almost nothing, almost instantaneously. That means large delta E is allowed during a tunneling because there's no time thanks to this uncertainty principle. Okay, so just apply this concept. Our Feynman diagram changed like this. So particle A coming to this, and another particle A coming to this. And here we have a region where the energy is under the barrier. That means here our particle is just along with the imaginary time. So therefore, in this way, almost no real time. And then you have a large space to interact with the electrons, and many electrons can come out because this is just an electron scattering. It is called off-energy shell scattering. And this scattering cross-section is very huge. And if the deuteron move every, let's say, less than 100 picometer, scattering can occur. That means all the electrons involved are scattered. So therefore, the conduction electrons can be changed to energetic electrons just in this virtual stage. I would say a pair of proton and deuteron in tunneling motion during imaginary time, reaction energy transfer to many electrons. Reaction region is much larger than nuclear cross-section, let's say less than. Nuclear cross-section is just like that. So just I pick up a point that might be important. Of course, the reaction probability, it's a very complex process, but anyhow, it might be proportional to the density of a proton, square density of protons, and the electron density, and the transmission coefficient, and a kind of a S factor, and also phase space, including the multi-electrons. That means rho E dominates not only the number of energetic electrons, but also the screening energy. So what is needed in this picture, high electron density and high hydrogen concentration. The another thing in tunneling motion, I found that proton is far more advantageous than deuterons. That's a behavior of a transmission coefficient. I calculate this just like this. Sorry, I'm almost running out my time, Yamura-san. So then I can switch to the imaginary time. So this large enhancement over the deuteron-deuteron transparency might compensate for large difference of coupling strength. We know the coupling strength of weak interaction is something around 10 to minus 5. So it can be easily compensated if you have a 100 electron volt, then the enhancement over the DD case is 10 to 12. That is second point. And the lower the energy, the greater the probability of electron scattering, because the electron scattering is essentially the Coulomb scattering, and this obeys just this. Therefore, the more electron involved in scattering, the more advantageous. Sorry, I just show the almost final one. And this is the apparatus of the setup being prepared right now. We have a foil and a thermocouple here and a heater. And the sample is a nickel carbon composite foil. And in this method, to make excess heat, we should listen to the Yamura-san's talk, which is on Thursday at 12:30. So we have a soft X-ray detector and also the spectrometer system of visible light. And this is very cute. I mean, the spectroscopy by, let's say, mini spectrometer. This is a Hamamatsu the technology. It's very small, so light comes in, we gather the light and transfer to this very small mini spectrometer. It's just a 12 millimeter and a 10 millimeter and 12 millimeter. Such a small thing. And I hope we can get the data as soon as they are ready. Thank you.
Any chance you can get a beryllium window on one of the chambers with the nanomaterial in it? You showed a picture of a beryllium window for soft X-rays. Is it possible to build a chamber for the nano materials?
No, it's impossible. We put a beryllium window.
Right, so you have a foil that you're looking at here. The question is, in light of the talk that Professor Takahashi gave, these nano material look like they're very interesting. And so the question is could that be assayed with your soft X-ray detector?
Well, for the purpose, we put the software X-ray detector is just measure the bremsstrahlung. Of course, there's some of the atomic, atomic transition of X-rays, characteristic X-ray, we can see that also.
Right, but you'll get a bigger signal perhaps from the characteristic X-rays, which the soft X-ray detector would be sensitive to. The SSD detector.
Well, we will assess.
I have a question about Bremsstrahlung electron detections. So you were making already last year some measurements of the spectrum, and is it possible from that measurement to just say that does this data match Bremsstrahlung or not, to know without assumptions whether we have Bremsstrahlung electrons? That's the first question. And second question, with the...
Yeah, of course, using the larger detector, you can do it. But if you're using the larger detector, background level is getting much higher and higher. So therefore, using the very thin detector, small detector, is more advantageous to look at a continuous radiation. That's the answer.
So you cannot say today whether there is Bremsstrahlung electrons, not yet.
Yeah, we want to see the real Bremsstrahlung spectra by using this system.
And the second question, for the visible light spectrometer, did you measure any peaks or did you make any measurements so far or not yet?
Well, this is the first experience for us, and not yet started, almost started, maybe 1 or 2 weeks later than today.
Okay. Thank you.
Maybe just a comment. We observed that increasing the neutron flux using pulsing toward atomic deuterium, it improves the results. So it seems it's not too far from your idea. It's correct?
Well,
just observation. Our it's not. We just observe. As large as possible electrons, as large as possible coming deuteron from the Constantan out.
Yeah, I agree.
Okay.
Any questions? Okay. Thank you very much.